In this video, we're going to go over section 7.1 from our textbook, which is on functions of several variables. So we'll start with an example here. Suppose a small manufacturing company produces a standard type of surfboard. If the fixed costs are $500 per week and the variable costs are $70 per board, the cost function is given by this guy here. Okay, we have our fixed costs here, and then our variable costs depending on the number of boards produced per week. So this is a function that is dependent on x, which is a single independent variable. Now suppose that the company decides to add a high-performance competition board to its line. If the fixed costs for this board are $200 per week and the variable costs are $100 per board, then our cost function is modified slightly to this guy here. So we have an additional $200 per week of fixed costs, so that's where the $700 comes from. We still have our variable costs for our standard surfboard, but then we're adding on the variable costs for this new competition board. So in this case, our cost function is dependent on two variables, x and y. And so this is an example of a function with two independent variables, x and y here. So a function of this form here, this is a standard example, is an algebraic expression in the variables x and y, and like we said, x and y are the independent variables, and this z here is our dependent variable. Z is dependent on the variables x and y. Now we can define functions of 3 independent variables, like w for example, or 4 independent variables, and so on in a similar manner. Let's look at some examples of this. So we're going to evaluate a cost function of 2 independent variables. Given this cost function here, we want to find c of 20, 10 here. So this means we want to find the cost function when x is equal to 20 and y is equal to 10. Doing so, we'll plug in x and y into our cost function. And then evaluating this, we'll get 3,100 here. Okay, so not too bad. Let's look at another example. We're going to evaluate a function of now 3 independent variables. So for this guy, we'll do the same thing here. We're given a function that's dependent on 3 variables, x, y, and z. And we want to evaluate this when x is equal to -2, y is equal to 2, and z is equal to 3. So we'll plug these values into our function here. So here we'll get 8. Here we'll get plus 12, plus 9, and then plus 1. All right, so this will give us 30. All right. Moving on to the next example, we're going to look at this in terms of revenue, cost, and profit functions. So suppose the surfboard company that we discussed earlier has determined that the demand equations for its 2 different types of boards are given by P and Q here. So P is the price of our standard board and Q is the price of the competition board. X will be the weekly demand for the standard boards, and then Y is going to be the variable for the weekly demand for the competition boards. So what we want to do is find the weekly revenue function and evaluate that guy when X is equal to 20 and Y is equal to 10. So doing so, first off, we know that our revenue function is the demand times the price function, right? So for this guy here, it'll be the demand for the standard boards times the price function for the standard boards, plus the weekly demand for the competition boards times the price for that guy. So this will be our total revenue for the 2 different types of boards. Plugging in our values for P and Q here, we'll get this here. All right, and then distributing this x to every term here and this y to every term here and simplifying a little bit, we'll get we'll get 220x minus 6x squared plus 4xy plus 300y minus 10y squared. All right. Now the next thing we want to do is evaluate our revenue function when x is equal to 20 and y is equal to 10. So plugging in these guys here, we'll get this here. All right, and then evaluating this will give us $4,800. All right, and then part B of this question tells us if the weekly cost function is given by this here, we want to find the weekly profit function and evaluate this guy here. So remember, our profit function is equal to our revenue minus our cost. Right? So we know that our revenue function is given by this guy here. So this is our revenue function. And then we were told that our cost function is given by this guy here. So subtracting that out, all right, so we'll simplify this a little bit. We know that this minus sign is going to distribute to every single term here. Combining like terms, we see that we have a 220x here, and then we'll have a minus 40x. So this will give us 180x. Then we have minus 6x squared. There's no terms to combine that with. Similarly for the 4 times xy. We do have a 300y and then a negative 80y here. So that'll give us 220y. And then we have this minus 10y squared and this minus 1000 left over. So this is our profit function. And now we want to evaluate this when x is equal to 20 and y is equal to 10. Doing so, plugging in the values for these guys. And evaluating this, we will get $2,200. All right. The next example we're going to look at is this one here. Suppose a company uses a box with a square base and an open top for a bath assortment, and that's shown in this figure here. If x is the length in inches of each side of the base and y is the height in inches, we want to find the total amount of volume and evaluate this guy here. So I just want to make a quick note here. If we want to find the volume of a box, it's usually dependent on 3 variables here, and it's given by the product of these guys. And so this is what this looks like visually. X is the variable that represents the length of our box, Z represents the width, and then Y will be our height here. So usually this is what we'd use to find the volume of a box. However, in this case, we know that our box has a square base. So in this case, our length and our width are equal. So that's why the volume will only depend on the variable x and the variable y here, since these guys are equal. So our volume is only dependent on those guys. And we can think about this in this case as x and z being equal. So we still have to multiply this guy by this guy by this guy here. So the length times the width times the height. So this will be x times x, so we'll get x squared times y here. So that'll be our equation for the volume of this guy. And now we want to evaluate it when the length and the width is, the length and the width is 5 and the height is 10. So this will be 5 squared times 10, which is 25 times 10. So we'll get 250. And this will be in cubic, since we're looking at volume, and then inches. Those are our units given here. All right, and then the last example we're going to look at is this one here. Given this function here, we want to find this guy here. And so you may recognize this as the difference quotient that we've seen in previous sections, but it's slightly modified here. We have this f of x plus h comma y. So this means we're going to evaluate this when x is equal to x plus h. So what I mean is, this guy is going to be equal to our function when x is equal to x plus h minus our f of x divided by h. All right, so evaluating this here, we'll get 5 times x squared plus 2xh plus h squared. We have a plus 9y squared minus 5x squared minus 9y squared. And this is still all over h. Notice we have a plus 9y squared and a minus 9y squared, so these guys will cancel. Then distributing this 5 to every term here in our parentheses, we'll get 5x squared plus 10xh plus 5h squared. And then we still have this minus 5x squared here. All right, and we still have that this is all over h. And we have a minus 5x squared and a positive 5x squared here, so those guys will cancel. We also have an h in both terms of these guys here. So what we'll do is pull that out. So we get h times 10x plus 5h all over h here. Now we'll have that these h's will cancel, and then we're just left with 10x plus 5h. All right, so that was an example of evaluating the difference quotient when our x is slightly changed here, but we still have our y with a function that is dependent on two variables, x and y.